We start to talk about serious things now. We are in theory of adhesion. You will see that the adhesive is always applied in the liquid state and then hardens. So let's see now the theory of adhesion. First of all, the forces involved, the surface roughness and the phase change. In the theory of adhesion, we are going to understand in which conditions we have a strong bond between the adhesive and the adherent. First of all, let's talk about the forces involved. You have two types of forces. You have the primary one and the secondary one, or the chemical one and the physical one. Primary one, it's very rare to have in adhesive bonds. I'm talking about the ionic, covalent, metallic. There is a change of electrons between atoms. It's very rare. You need an adhesion promoter to have primary bonds. In general, what you have is secondary bonds, van der Waals forces basically. And within these secondary bonds, you have of two types. You have the polar ones and you have the dispersive ones. This is related to the asymmetry of charge in the atom or molecule. You always have some part of the atom that is more positively charged than the other part that is more negatively charged. And this, of course, causes attraction between that atom and other atoms or molecules. When the asymmetry of charge is permanent, then you have polar bonds. When the asymmetry of charge is just temporary, you have dispersive bond. Of course, what you want ideally is to have a lot of polar bonds. They give you stronger joints. But there is one thing that is common to all the forces involved, whether they are primary or secondary, is that they are very short distances forces. That means that if you want them to enter into action, you really need to approximate them very, very, very closely to each other. We are talking about 10 to the minus 10 meters of the order of angstrom, really a fraction of micro. And if you look on the other hand at the surface roughness of substrates, you will see that really it's highly irregular. One way to calculate the average of this Hx is to calculate the roughness. And this roughness can vary a lot. It can vary from very crude cutting to very fine polishing. But with all of them, we are still talking about a small fraction of micron, not this type of distance. So really what happens is that when you imagine that you want to bond an adhesive to a substrate, the adhesive is solid, it's impossible that the two will match. It's like putting two mountains on each other. They will match only in a small number of points. And this is nowhere enough to create a strong bond. Ideally, you want the adhesive, when you put it in contact with the solid substrate, to match perfectly all the area of the substrate. Otherwise, there is not enough secondary forces to withstand the load applied. How can you guarantee that the adhesive will contact intimately the substrate? The only way is to apply the adhesive in the liquid state. Then you can have a perfect contact between the adhesive and the substrate. That is why the adhesive is always applied in the liquid state, so that we have a perfect match and a lot of van der Waals forces, okay? Okay, so this is nice. We applied the adhesive in the liquid state, but then you need to harden it because a liquid will not stand any load. So that's the second part of the second step in the application of this technology. First step, application of the adhesive in the liquid state. Second step, phase change, hardening, curing, all right? And there are basically three ways the way adhesive can harden. You can have a loss of solvent. This is typical in the white glue for wood. The solvent will evaporate and you will be left only with the hard parts. It can be from cooling from the molten state. In the case of the Holtmets, we are talking about thermoplastic adhesive. So you heat, you apply the adhesive, it's liquid, and then it will cool down, and this cool down will harden the adhesive. And finally, you have a chemical reaction. You have a resin, you have a hardener, you mix them, and this will cause a chemical reaction that will harden the material. In general, structural adhesives, they cure by a chemical reaction. I can show you quickly with an adhesive that you can buy in every shop. It's super glue. It's a cyanoacrylate from the family of the acrylate adhesives. The two phases: first the application of the adhesive in the liquid state, and then the hardening. Fortunately, it's done in seconds, so you don't have to wait a lot. And I'm sure you have done that at home, but you didn't know probably why the adhesive needs to be applied in the liquid state. It needs to be applied in the liquid state so that it will create a perfect bond with the substrate, a perfect match with the substrate. So I put just a tiny bit of glue, liquid, and then I put the other substrate, and the hardening is done in seconds, as you know. You have done this at home many times. For some adhesives, you have to be careful not to put too much, because if you put in your fingers, then it will glue your fingers. But you know, everybody knows that this takes seconds. So you wait a few seconds until you have hardening. During this phase, you have a chemical reaction, okay? Chemical reaction is happening at the moment. The adhesive is slowly curing. And when it's cured, then you have a joint that is solid, the adhesive is solid, and hence strong, okay? So, in this first part of the theory of adhesion, you have seen the fundamental first steps when you apply adhesive. First of all, it needs to be applied in the liquid state so that it creates an intimate contact with the adherent. And second, it needs to change its phase from liquid to solid so that it can withstand the load.